I'm Charlie Hawk, CEO of Bluespec, and I'm here with my colleague, Joe Stoy. And we're going to describe our experience in integrating the CV32 core into our RISC-V Explorer product, which is a free tool that we've released just recently to help people evaluate RISC-V cores. So let me give a little kind of background, and well, let me share my, my screen as well. So let me give a little background on what Bluespec Inc. does and what we do with RISC-V. So we provide tools and IP to help customers safely and efficiently use RISC-V open source hardware. So what we do is we see in this diagram here at the top are the GitHub repositories for all the best open source RISC-V hardware projects. We take those projects, we bring them into Bluespec, we configure and generate cores. We integrate them into real hardware and software systems, and then we verify and validate them. And from that evaluation process, we curate the best cores that are available from open source. And we suggest these to the people interested in using RISC-V cores. We're very agnostic about the best cores that we curate. It's just the best core wins for whatever the application is. So in addition to that, we provide then for any customers that are interested in a particular family of core or configuration, any of the missing productization and support that might not be available from a free open source repository. And so we produce a Bluespec silicon IP package, which provides, like a typical silicon IP package, a synthesizable Verilog, verification, reference designs, and reference software, and tool chain integration. And so basically what we provide are best-in-class open source cores that have the quality of a proprietary IP package with all of the open source benefits. And what we mean by that is we don't add any restrictions onto the use of the code for the open source core itself. That core, once it's made available, can be used without restrictions, without any type of royalties or other types of licensing fees that are required. Now, everything I just explained pertains to the demand side of RISC-V open source hardware. So we also plan to help to benefit the supply side as well. And so what we'll be doing is transparently publishing core rankings based on our internal and independent apples-to-apples evaluations of the RISC-V open source cores. And what we hope to do by that is enable vigorous competition between these open source projects. So for instance, one of the projects we work with is the Chromite cores from Incor. And we can see kind of a very kind of, great reaction in terms of if there's a core, and if one of their cores in some way doesn't particularly match up with other cores, they take action to go and to remedy that. So that what we plan to do then overall is provide kind of unbiased credibility, independent credibility to RISC-V open source cores so that they can effectively compete with proprietary cores and eventually take over proprietary cores as the major source of cores for RISC-V users. So that sets up what we're doing with our free RISC-V Explorer product. We released that on August 26th, and that's a very concrete step to providing this benefit to both the demand and supply side for RISC-V cores. So the RISC-V Explorer basically consists of many pre-built, pre-tested RISC-V cores selected from the major families, as we mentioned before. Will provide different combinations of ISA extensions. So the version that we just released was an RV32 IMAC edition for the RISC-V Explorer. And what that means then is of that combination, we provide all of the subsets of that, like RV32I, RV32IM, IME, and IMC. In addition, we provide for each of those cores some number of different memory systems. So initially, we provided probably about 8 different versions of caches from different cache sizes and different cache associativities. And in the future, we'll be populating that with tightly coupled memories as well. So that first release we had over 225 cores. The important thing to note here is that this is like push button access. You don't have to build anything. and you don't have to assemble anything. So you could, within literally seconds of downloading the free RISC-V Explorer, you can be up and running software and doing various other kinds of evaluations of the core itself. So the primary goal here is with pre-built simulation and FPGA binaries is to enable software evaluation. That's done with pre-built RISC-V tool chain. You can compile and run canned program examples like Hello World and CoreMark and FreeRTOS, or you can take those templates that we provide for those programs and modify those to compile your own code and evaluate that code. In addition, we provide lots of pre-characterized performance and size data so that you can compare the implementation quality of the various cores. And as I mentioned, but we have 225 cores now, which span Rocket, Piccolo, and Flute. The topic of this discussion is the experience we've had in adding the the CV32 E40P processor to this, which will be released sometime around the end of September. And what this shows is kind of a very kind of quick way to get up and running with RISC-V. Now, given that there are so many cores, and there will be many even more cores as we start to do future releases, we provide a fine core, which is a Linux type capability that allows you to sort through cores for various parameters like gate count or core marks, and then also kind of rank the cores based on that to help people quickly kind of navigate through all of the available cores. So this is the SoC that's inside the RISC-V Explorer. So in the green box, that's where we plugged in the CV32 processor. This is a fairly standard SoC that primarily provides a JTAG interface for debugger, UART interface for a console. In the future, it's not in the current release, but in the future, we'll have Ethernet capability as well. And then there's all of the memory subsystems that are required, like DDR3 in the case of the RD board that we're making available with the first release with the first version of the FPGA board with the Explorer. We're providing on-chip boot ROM and a flash controller. And so this is a complete subsystem for doing software evaluations of the RISC-V cores. Again, push button and just out of the box. Okay. So this is the CV32 E40P_SS, which is the complete system that was presented to us by the Open Hardware Group. You can see the CV32 E40P, which is the basic pipeline for the processor itself. That goes into an OBI type of fabric type interconnect, which then ultimately provides 2 AHB master ports out to the SoC fabric. And so these 2 ports that we see right here going onto the fabric right here are the equivalent of these 2 ports at the bottom. Now, in addition to that, there's the debug module and there's the JTAG tap interface to provide the full debug capability. So the components in the red box were not available. So what Joe Stoy did was he proceeded to provide our own switch fabric, which was an AXI4 switch fabric, to basically build that same capability. And inside that switch fabric, that's how we connect to things like the PLIC and the CLINT. And then also, while we were able to get the debug module from the Pulpissimo data repository, we used our own JTAG transport module because that was up and running already with the Explorer. And so with these 2 modifications, we were able to fairly quickly get the CV32 core up and running in the Explorer. So let's just look at some initial comparisons. We've got, again, these are against the 3 families of processors that we have in the Explorer right now. So when we add the CV32, that implements RV32 IMC. All of the others are IMAC. The CV32 has 4 pipeline stages, and the others are 3, 5, and 5 pipeline stages respectively. And there we list the core marks as well. Okay. Now, that core mark was something that was generated using caches with the CV32, which didn't come with any type of memory system. But we connected caches to that system so that it would be an apples-to-apples type evaluation against Piccolo, Flute, and Rocket. We did some 45 nanometer analysis on Piccolo, Flute, and Rocket as part of what we provide for the Explorer. But in this case, it wasn't available. We weren't able to do that yet for the CV32 because Yosis, which we use as the open source synthesis tool, doesn't yet support some of the system Verilog language constructs that are necessary. Now, we've also done analysis on UltraScale Plus, which is a VCU 118 board from Xilinx that we use. And here's the comparisons on the LUTs. And what you can see is that overall, the CV32 is kind of in the ballpark of the other cores that we have. You know, certainly it's got a higher frequency and higher LUT count than Piccolo, which has got a three-stage process, three-stage pipeline versus a four-stage. But it's pretty comparable to the others. The Flute core, we've done quite a bit of optimization on recently. We haven't looked at, you know, what some of the idiosyncrasies might be about compiling the CV32 in the FPGA. So over time, we expect as we continue to update the results that we get from the internal Explorer evaluations we do, we're going to be publishing new results as they become available. And we expect that as we gain more experience with the CV32, these improve. So now what Joe's going to do over the next 10, 15 minutes or so is show some demos of the CV32 on the RD A7 FPGA board. So this is a very similar to the FPGA board that CMC provides. And it's about this version, which is the A100, is about $249. There's another version, which is about $149. Again, what we've done is we've added 4 kilobyte caches to the processor. And then first thing Joe will do is just show, like, you know, RISC-V ISA test running and FreeRTOS, just to show that all of the work that he did was functional. And this was a pretty kind of straightforward bring up of the core. The next thing he'll show is he's got an LED kind of color application, in which the color changes indicate, you know, some level of microarchitectural performance, how fast the processor for a given fixed 25 megahertz frequency at which this is running at is actually kind of, you know, processing the code itself. He'll show some interesting results there, and then we'll follow up with, you know, what Joe shows on that LED color with the comparison of the core mark between Piccolo and the CV32. And then just the other thing is, so the CV32 without caches, we have that running in simulation. It's about, you know, 20 to 30 times slower than the case with caches. So one of the important things here to note is that caches matter. And then the other thing is, and that's going kind of straight to the DRAM through the fabric. Now the other thing is we don't have that. We're still debugging that in the RD FPGA. There's some type of bug that we've run into, and as soon as we fix that, we'll have that up and running as a demo example as well. But with that, Joe, maybe I'll hand off to you now, and I think I'll just stop sharing. And
hi there, greetings from a sunny but cool Cape Cod. Having greeted you, let me immediately stop my video and share my screen. What I hope you can see is the RT-A7 board on the left of the screen. As you see, it's very similar to the Nexus board. I think it's got somewhat more memory and somewhat fewer I/O facilities. And now I've got that on the screen, I'm going to turn the camera's exposure down a bit so that it emphasizes the lights, which are the only interesting thing to look at really once we get going. The first thing, to show that the thing is functional, I'm going to run a test program and ask it to run the ISA tests and the FreeRTOS test on the CV32E40P processor. So we'll see that, first of all, programming the bit stream, and you'll see the light at the top go out temporarily once it gets going. Now, why hasn't it got going? Yes, here we go. And yes, now, so it's programmed the bitstream, and now it's running the ISA tests. The Python program that's running has a table for every processor supported, giving the exact architecture of that processor, and it's choosing from the several hundred ISA tests only the ones that are relevant to the architecture. So that's going through now. Slightly slower than I'm used to, possibly because of all the Zoom calls that are running on the same laptop. And when it's finished this, it will compile and load up the Blinky test, which is a standard test of FreeRTOS. Here we go. So it's starting the GDB connection. It's now compiling the FreeRTOS with the Blinky test. And now it's running it. And it's passed it. I don't know if you can see on the board, there's a yellow light flashing there. That's saying that although the Python program has finished, the FreeRTOS is still running in the board, and the little yellow light says it's transmitting stuff on its UART. So if we put a terminal emulator there, you can see that IO is still going. Well, the next thing I'm going to do is instead of resetting the processor, it's easier to reprogram it. So I'm going to do that. And you see the once it gets to it, the program light at the top left-hand corner goes out temporarily as the new bitstream comes in. And now we can go to the next part of the test. So I go to the directory in which we run GDB. And what's happened there is that GDB in the laptop, under that control of that script init32, has connected to the debug module in the ARTI board. This is the pulp debug module, as you saw on Charlie's slide. And I'm going to run the tests which Charlie mentioned, unimaginatively called RT1. And I'm going to load that into the board. That went across the JTAG connection from the laptop into the FPGA. And now I'll start running it. And what's happening there is that this program is, for each step, changing the configuration of the LEDs at the bottom of the board. Not very aesthetically, but there you are. And also counting the number of clock cycles taken to execute each step. The board is running at 25 megahertz. It could run much faster, but at this stage of the game, keeping Vivado synthesis times low is a good thing. And so you see the duration of each step is 13 million or so, just over half a second at 25 megahertz. So for comparison, let me throw that off and go back to program our Piccolo processor, which we call Bluespec P1. And again, the light will go out when it starts loading the bit stream. There it is. It's the new bit stream's there. And so I'll go back to the simulation directory, run the same GDB, the same file, load it and run it again. And you see now Piccolo is running, and it's running slightly faster, 12 million rather than 13 million, so slightly faster than half a second. So that's saying that the processors take slightly different number of clock cycles to execute the same step in the same program. To get a little more quantitative about that, again, I will throw it off. And sorry, I didn't actually need to throw it off, because I'm just going to change the file I'm going to load, which is the CoreMark program. Now remember, we've got Piccolo in the FPGA at the moment. So if I, what I'm going to do actually before I actually run that program is to increase the size of the terminal window. And you see CoreMark has run. It's run very quickly. It thinks it's run for 12 seconds. It hasn't. So that configuration is slightly wrong, but CoreMark is, as long as it's got sufficient ticks, which it has, it's happy. And you see the score is 2.64 megahertz. I forgot to set the breakpoint, so let's see if we can change that. So that's 2.64 for Piccolo. Now I'm going to go back to program the CV32 again. Here we go. Sorry, Vivado always takes its time to load. Vivado Lab. And here we are. So back to this and the same file as before, loading it. This time I will set the breakpoint, and if I run it, you get 2.23. So it's a slightly lower performance, only slightly. Perhaps I should mention that in simulation, these numbers come out a little higher, by about 0.03. So this would be 2.26 in simulation, slightly better. And that's because in our very latest simulation, our model of the memory hasn't accurately allowed for the delay in the DRAM memory. So it's rather faster than the actual DRAM memory is on the board. I should also say that if we run this CoreMark in simulation on the version without caches, the CoreMark score goes down to 0.34 or something like that. So as Charlie said, for this kind of test, caches are important. But as you saw perhaps from the slide, the connection to the memory goes through several fabrics. So again, it's a matter of horses for courses. If you have a tightly coupled memory nearer the processor, then maybe caches are less important and so on. Anyway, that is the conclusion of the demonstration. So I will hand you back to Charlie.
Okay, and Rick, that's the conclusion of our presentation. If you want to go into questions.
Yeah, great. Thanks, Charlie, and thanks, Joe. Appreciate your insights and your support for the Core 5 family. We didn't get any questions that came in through the chat window. How would users contribute to, either improving the results or exploring different integration options into your platform? Maybe is a question that you could answer.
Yeah, I mean, they can. We can just work with them. There can be, integration options that show up in various open source repositories, and we can start to add those to what we put into the Explorer itself. So we're open for lots of inputs on the right ways to compare cores and the right ways to do that to get the whole open source community competing with each other much better.
Right. Sounds good. Okay. Thanks very much, guys. We'll transition in a moment here into our next talk. But thanks for your talk today and for joining OSD Forum.